session of the second day. First off, we've got Jere Koskela, who's going to be talking about non-reversible MCMC for discontinuous targets and disconnected spaces with boundaries.
All right. Thanks, Emma, for the introduction. Thank you to all of the organizers for inviting me. It's been a pleasure to attend this workshop. I've not had a great amount of exposure to neutron transport before, and I feel like I've learned a lot, so it's been a great experience. I want to, the main bulk of my talk is on non-reversible MCMC, and I'm going to speculate a little bit at the end on how it might connect with applications for the sorts of equations that we've been seeing over the past day and a half. In particular, I want to focus on, as the title suggests, non-reversible MCMC on settings which are in a sense awkward in that they're not smooth Lebesgue densities on connected domains. So I have a motivating example for this, which I'll introduce throughout the talk as well, which is the Kingman coalescent process in genetics, which necessitates such an approach. It doesn't have such a nice Lebesgue density as a target posterior density for Bayesian inference. But I also want to make the presentation a bit more general. And it turns out that dealing with a variety of phenomena, namely, it's probably a non-exhaustive list, but in the very least, you can think of processes, sort of hybrid processes, which have both discrete and continuous parameters. You can think of processes defined on state spaces which are discontinuous, and also state spaces with boundaries. And the kind of approach for dealing with all of those things turns out to be relatively similar. So I've grouped those together in the title. Here's a somewhat more specific outline. So I'll briefly introduce the basic zig-zag process, which is a continuous time, non-reversible Markov chain Monte Carlo method. It's been around for a few years now, and it's gaining increasing prominence, I think is fair to say. But I'll spend a couple of words on explaining what the basic process is, and then add in this complication of living on a hybrid state space, which has both discrete and continuous parameters, and it'll be clear from the construction that the same thing works for state spaces with boundaries as well as disconnected sets. Then, once the algorithm is in place, I will introduce the coalescent process just as a kind of worked example. So this is a gold standard model in phylogenetics, modeling the common ancestry of samples of DNA sequences. And I'll introduce the process, write down the form of a posterior distribution under this model, and then demonstrate that indeed this setup for setting up zigzag processes on complicated state spaces works nicely for the coalescent. In particular, in the coalescent setting, you're trying to integrate over a latent space. So you're doing data augmentation. You would like to observe a whole ancestral tree for your sample, but the tree is missing. So you're trying to evaluate an integral over a space of trees, which is why the domain is somewhat awkward, and you require this kind of hybrid state space approach. And then at the end of the talk, I will briefly try to connect this to something which might be applicable to these neutron transport equations, only on the level of pictures and conjectures. I don't have anything concrete to say there, but I think it does at least suggest that there could be a place for these types of algorithms, and that you could kind of deal with the kind of discontinuities at boundaries and so on that you expect on target distributions arising from these nuclear reactors we've seen. The kind of the construction of the domains seems to have a lot of jump discontinuities and so on in them in terms of control rods entering the picture and all of these things. And I think this could be a promising framework for handling those sorts of phenomena if one wanted to run a non-reversible MCMC chain for one of these reactors. So this is a one-slide introduction to the zigzag process. As I already said, it's a continuous time MCMC method, and the interest is in sampling from a target density pi, supposing that this is just a Lebesgue density on RD for the moment. And the algorithm proceeds by augmenting the state space with velocities. So in the simplest case, I just take binary velocities in each of my coordinate directions. And then in continuous time, I iterate the following loop. So while I haven't yet hit my target terminal time, I'm aiming to propagate my algorithm with constant velocity v in the direction that the velocity is pointing. And I'm aiming to simulate flipping times at which I flip one of the coordinate velocities. And this lambda I is my notation for one of these flipping times. So these first two lines are just a semi-explicit way to construct samples with the correct exponential rates, lambda I, at which various flips happen. Here I propagate my algorithm, so my spatial variable progresses until time rho with velocity v. The algorithm time increments, and then whichever clock rang first at whichever of these flipping rates, I flip that corresponding element of the velocity vector. And provided I can do this simulation step in the first few lines, then it can be shown that if you set up your flip rates with this correct expression, which involves the velocities and the gradient of the logarithm of pi, then pi is indeed an invariant distribution of this algorithm. And here you already see the kind of hiccup that enters the situation if your pi does things like feature discrete variables, like feature discontinuities or other sort of boundary phenomena, namely that this gradient of the logarithm of pi may not have an obvious definition. So at a minimum, you have to make sense of what you mean by something analogous to this if you want to even implement the algorithm with these kind of flip rates. Before I go into that, however, here is a brief illustration of what a sample path from a zigzag algorithm looks like. This is a picture that I have reproduced from the paper by Joris Bjerkens, Paul Fernhead, and Gareth Roberts, where they really fleshed out the zigzag algorithm. And over here, the target density has these S-shaped contours. So this S that you see on the picture is roughly the kind of mode, if you will, of the target distribution, and it's quite an awkward shape. And you can see that it would be quite difficult to write down a Metropolis Hastings algorithm, which did a good job on a distribution of this kind of shape, because unless you have very detailed information of where this manifold of high probability is, you can't write down a good proposal distribution for this. Whereas the zigzag algorithm, essentially what it's allowed to do is it travels in a fixed direction, and it does so, and it keeps going in that same direction for as long as it's hill climbing. So as long as it's progressing into a region of higher probability, then these flip rates on the previous slide will evaluate to 0. And only when it starts going downhill, down the density profile, the flip rates become positive. And so at that point, it will eventually flip. And so it's able to find these kind of long contours of roughly constant or positive probability and actually progress along them in an efficient way. And that's one of the motivating advantages of why these kind of zigzag and non-reversible processes are nice. This is still an incomplete list, but just to name a few more. Reversible algorithms, Metropolis Hastings and most others that people are familiar with, are invariably reversible, and reversibility inherently comes with a certain kind of tendency to backtrack on yourself. You obey detailed balance, so locally you're equally likely to step in one direction as you are to perform the reverse step in the opposite direction, and therefore you tend to have this sort of diffusive behavior where you wiggle back and forth back in on yourself. And if you're not reversible, then you have at least the potential to avoid that kind of backtracking behavior and be more kind of decisive in exploring a particular direction at a time and getting around your state space more rapidly. This formulation that I've shown you is rejection free. You don't waste any computation proposing moves which don't progress you anywhere along your state space. course, if I flick back a couple of slides to over here, I have said that you have to be able to simulate times with these rates, lambda I, and that's frequently done with Poisson thinning. So you are still introducing rejections into the algorithm. In that way, you find some dominating intensity for this flip rate and simulate from that and thin down. But even then, the algorithm still keeps moving. So a rejection doesn't mean that you don't move anywhere. It just means that you move a little bit and keep moving further. So in that sense, this rejection freeness means no wasted computation. And you're exploiting the shape of the target to make educated moves in your state space. But yeah, as indicated, there are downsides. In particular, the construction only makes sense in a relatively restrictive set of problems, at least in comparison to something like Metropolis-Hastings, which can be implemented for almost anything. It may not be efficient for almost anything, but it's usually fairly easy to sort of get an idea of how one might implement it for a problem, even if the state space is complicated. And yeah, also if the state space is not a connected set, then these continuous time, continuous path dynamics won't be able to traverse you through any gaps or anything like that. So how might one define an analog of a zigzag process for a hybrid state space, which is my terminology for a state space which contains both continuous coordinates and discrete coordinates? I want to split my target pi into two halves. M is going to be a countable parameter, so that will encode all of the discrete coordinates that I'm interested in. X will continue to denote continuous coordinates on some subset of Rn. And the trick will be that for each possible value of my discrete parameter, I create a copy of this state space of the continuous parameters. And it'll be the occupation index of which copy I'm in, which will determine what value, the state of M internally for the process. This next bullet point is somewhat involved. There will be a picture on the next slide which illustrates it more fully, but let me just try to get through what the definition is before I get to that. I want to introduce boundaries into my state spaces. So each of these omega m's will have specific sets in them through which I exit that particular copy of the domain, and another set through which I enter the domain. And these sets will be dependent on velocities as well. So if you think of omega as being a bounded domain, it has some piecewise Lipschitz boundary, for example, then gamma plus will be the combination of positions along the boundary and velocities pointing out of the set, so that in the next instant of time, my process would exit this particular copy of the state space. And the entrance one, the gamma minus, will be same thing, except that the velocity is pointing inward. So gamma plus will be the points through which the zigzag process would exit a region. Gamma minus will be the ones through which it can enter. While in the interior of one of these sets, my zigzag process will undergo the exact same zigzag dynamics that I've just introduced previously on the restricted target density, where this discrete parameter is fixed at the value it's currently occupying. And all that remains to do is to specify what happens when it hits one of these gamma points. And I'll do that momentarily, but before I get into that, here's that illustration that I promised. So here I take a very simple case. My continuous variable has domain just the unit ball, and my discrete parameter has only two possible values. And so I've created two copies of my state space, and here I'm taking the whole boundary to be the defining set for these gamma pluses and gamma minuses. And if I arrive at a boundary point and my velocity is such that it points out of the domain, then I'm trying to exit the domain, so that position cross velocity point belongs to gamma plus, and gamma minus correspondingly is those points at which the velocity is pointing inward. And so the updates of my discrete variable I'm going to want to make by saying that whenever my zigzag process enters a boundary point and has a velocity such that it's part of this exit boundary gamma plus, then I'll undergo some sort of jump. I can jump back into the same domain, I can jump into the different domain, but somehow I end up at a velocity at a spatial position, as well as a velocity which is pointing back into one of these domains. Put a bit more formally, hang on. Yeah, so that's this final bullet point. That's really the content of this final bullet point over here. When one of these exit boundaries is hit, I've got a user-specified jump kernel Q, which takes me from an exit boundary to a random point on the entrance boundary and facilitates the fact that my algorithm can continue even having hit a boundary. Just a couple of words on connections to existing algorithms. So there's kind of two similar settings in which zigzag algorithms have already been constructed. Perhaps the simpler one is one by Joris Birkens and co-authors who have actually written down a zigzag algorithm on a restricted domain with a boundary. So they were only looking at, for instance, one of these balls. And for them, whenever they hit the boundary, this jump kernel Q just reflected it back into the interior of the domain, and they showed that still preserved the correct stationary distribution. And what I'm suggesting here with this more complicated user-specified jump kernel Q is just a generalization of that into a union of many domains, where you don't necessarily just reflect back into the same domain, but you can also jump into a different point on a different domain. And there's a second class of generalizations of zigzag algorithms, which are based around the notion of model selection. So there's two papers in particular by Chevalier, Fernhead, and Sutton on the one hand, and Gagnon and Doucet on the other, who wrote down zigzag processes for model selection. And for them, the discrete variable, they had a discrete variable in there, which was the number of non-zero variables. And they heavily used the fact that that gave their discrete parameter a very natural ordering. Namely, you could add one variable or subtract one variable in one step, and they used that in defining this jump kernel Q. And what I was most keen to do and most interested in doing was putting as little structure as possible on these discrete variables. And in practice, you'll probably still have to have that sort of structure in any particular case in order to have a realistically feasible algorithm. But this kind of leaves that part of the problem to the user and writes down, and the aim is to write down general conditions on the jump kernel Q, which you can check in each particular case to make sure that you have a correct algorithm. So for analyzing a process like this, a convenient set of tools is that of martingale problems. So I want to think in terms of generators and domains of generators. And indeed, this monograph by Davis on piecewise deterministic Markov processes provides exactly the right kind of setup for studying both the standard zigzag process as well as this hybrid zigzag process that I've introduced. And in particular, there is a theorem in Davis's book which says that the hybrid zigzag process is a piecewise deterministic Markov process which has the following generator. So here we have just motion at a deterministic velocity v in the x variables, the continuous variables, while the discrete variable and the velocity are being kept fixed. And then this is exactly the same velocity flips as in the standard zigzag algorithm, again with the discrete variable m being kept fixed. And the impact of these discrete jumps, the jump kernel Q arising from these boundary hittings, is left entirely to the domain of the generator. So the domain consists of functions which satisfy mild measurability and boundedness conditions, as well as the following sort of symmetry condition. So at each point from which I would exit a domain, my function f has to evaluate to the average across all of those points to which it might jump in the next instant of time. And of course, q is a user-designed parameter in this algorithm, so you have to design it in such a way that you can evaluate this integral and check that this identity makes sense. So that will be the framework for thinking about this process. So here's the theorem, which says that it still has the correct stationary distribution under verifiable conditions. There are some technical conditions, which I'll sort of gloss over briefly, that initial conditions have densities. I have to assume that the number of different possible discrete variables is finite. If it's countable, then that introduces further technical difficulties, which I've not overcome at this point. We need some continuity assumptions, but only on the interiors of all of these domains. So we can allow discontinuities at boundaries. And it's also worth emphasizing that the positioning of the boundaries doesn't have to correspond to any natural ones. So if you have a target pi which has a discontinuity, you can just turn that into a boundary in your problem. And so as long as your discontinuities are restricted to hyperplanes, to sort of nice sets or manifolds, I suppose I should say, to nice sets of measure zero, then you're in this setting. But yeah, these four are the kind of big conditions. So we need finite activity, number of jumps, expected number of jumps should always be finite. We need this skew detailed balance condition, but we don't need it for pi as such. We need it for the jump kernel q. So starting from a position distributed along according to pi on an exit boundary, and here on the opposite side, we're starting from an entrance boundary on a different domain, and then reversing all of the velocity coordinates. So again, this is something which you have to design q so that this works. Third part is just a conservation of velocity condition. So it says that these jumps arising out of these kernels q can't slow down your process or eventually grind it to a halt. And the fourth thing is I've sort of not said what happens if my process hits multiple boundaries at once or anything like that. So you have to be able to rule those out as events of zero probability. But essentially, provided that 2 and 3 and some technical conditions hold, then pi is a stationary distribution. I'll give a very brief sketch proof of how an argument like this works. The key is that the various technical assumptions on the previous slide guarantee that C1 bounded functions in the domain of the generator separate measures on the domain of the zigzag process. And so it's enough for me to check that the expectation of the generator applied to these functions vanishes. How does one do that? Well, this is just writing down the definition of the generator. Going from the first line to the second, I'm doing two things. I'm first of all plugging in the explicit definition of the expression for these lambda i's, which I had right at the start of the talk. And then I'm doing a quick change of variables to get rid of this. So this capital Fi of v just means the velocity v with the ith coordinate flipped. So I'm getting rid of the capital F to arrive at this second expression. And then over here, what I have is a grad f in the first expression and an f grad log pi in the second. And there's a very strong temptation to do an integration by parts to move this gradient over to the f, which is indeed the right thing to do. That gives you the third line. You have the first term minus itself and some boundary terms. And now from this point, there is a 3-line argument which uses the 3 kind of key assumptions that I've highlighted thus far: the symmetry condition for functions f in the domain of the generator, the skew symmetry of q and pi, the skew detailed balance rather of q and pi, and this conservation of velocity condition. And you use each of those once, and you can show that the boundary terms also vanish. And that is kind of the strategy for the proof. Let me mention a few words on ergodicity. Again, if I restrict to the case where the domain of the discrete variable is finite, then there are very natural conditions that give you not just the correct stationary distribution, but an ergodic process. So you suppose that the standard zigzag process restricted to a single domain is ergodic, and that the full process places enough mass on the boundaries so that it can cycle through all of the domains infinitely often. Then you get an ergodic hybrid zigzag chain. This is kind of a slightly cheating, this slide, because ergodicity for the standard zigzag process for just a single domain is still a somewhat delicate question. There are only partial results, and I think that it's fair to say the full picture isn't fully understood. So in a way, I'm just brushing the problem under the carpet and referring to the existing work by Birkens, Roberts, and Sitt. But it does sort of show you that at least in this setting of finite possible values of the discrete variable, you're not adding any complication when you move to this hybrid setting. Okay, so that was probably a fairly dense introduction into this hybrid zigzag algorithm. The following few slides I'm hoping will illustrate a bit more concretely how one might go about this and why it's useful, just by giving a concrete application, and in particular an application where there is no particularly natural ordering or other sort of geometry to exploit for this discrete parameter. And so these kind of fairly washy Q operators for the jumps really are necessary in order to define the process sensibly. So the coalescent is a model of common ancestry among genetic samples. And so you can think of it as a random process that builds a random binary tree. I start at time 0 with just n singletons. So these are just disconnected leaves that will eventually form the leaves of the tree. N is a parameter, it depicts the sample size, so it's a fixed constant set by the user. At each iteration, I sample a waiting time, which is exponentially distributed with rate k choose 2 while there are k leaves remaining. And when this clock rings, I pick 2 leaves at random and I merge them into a common ancestor and decrease the number of leaves by 1. So this draws a random binary tree where the times between merger events are exponentially distributed such that each pair of leaves or blocks is trying to merge at rate 1. And when you have a realization of this tree, you can use it to model genetic diversity by throwing down mutations along it as a Poisson process along the branches of the tree with some fixed mutation rate. So there's a picture of this on the next slide. So here I am starting with 5 leaves at the, at the right of the slide. I merge pairs of leaves at rate 1. So the first merger event happens here, and there's another merger event that happens over here, and so on until I reach my common ancestor. I throw down mutations, so I have some mutation rate, and these red dots along the branches denote mutations. And there are many different interpretations you could give to these mutation events depending on which bit of the genome or what kind of biology you're modeling, but the one I'll use for today is what's called the infinite sites model, which essentially says that each of these mutation events is assigned a location. So each of these horizontal lines here on the right-hand column is a chromosome, And each of these mutations happens at a uniformly sampled location along that chromosome. And so you can sort of see that these two mutations over here have to correspond to this one and to this one, because those are the two that are common to these two samples. And these two samples have both inherited these two mutations. Whereas this one over here, well, it must be this one because it doesn't appear on anyone else and it doesn't get inherited anywhere else along the tree. Similarly, this individual only has this mutation on it. This individual only has this mutation on it. This has none because it doesn't encounter anywhere along the tree all the way down to the root. And the biological problem, or the inference problem one often wants to solve for these sorts of things, is you observe this data set on the right, that's what the biologist gives you, but they don't know what the tree is and they don't know where the mutations were. And so what you would like to be able to do is evaluate the likelihood. This is probability of data, which is this data set over here, given some parameters, for example, the mutation rate, but you don't have access to that. The only way that you have to access it is by a data augmentation. You condition on the missing ancestry A, and you write it in this kind of way, probability of data given ancestry and parameters. This is a tractable expression. Probability of ancestry given parameters, well, this is specified by the law of the Kingman coalescent, and then you're integrating over all possible ancestors, which is an intractable integral essentially as soon as your sample size is bigger than 3. There are numerical tricks that can get you up to maybe sample size 50, but certainly nothing of the scale that we now have DNA sequence data for. Okay, so this process features continuous variables. It has these branch lengths in it, or the holding times between branch lengths is another convenient way to think of them. It has scalar rates, for example, the mutation rate, but then it also has discrete variables, these tree topologies. And if I give you 2 separate tree topologies, it's not particularly simple to say whether they're close to each other or if 3 tree topologies are pointing in the same direction. It's sort of the notion of a geometry on these things is quite complicated, which is exactly why I wanted that Q jump kernel to be so vaguely or flexibly defined, to put a more positive term on it, because that's what's going to facilitate mixing between tree topologies in a moment. So for the purposes of connecting this to the zig-zag algorithm, it'll be convenient to encode a realization of a binary tree as this tuple where Tn encodes the lengths of the branches on the tree, and it encodes it by storing the times between successive merger events. So T1 is the time from the leaves to the first merger event. T2 would be the time from the first merger event to the second merger event, and so on. And you can see, if I flick back to the picture of the tree, that if I tell you all the holding times, well, you can reconstruct all the branch lengths. And this En will take values in a discrete set, and it will store the topology of the tree, the ranked topology rather. So what order all the mergers took place in and which 2 lineages merged at each event. I'm not going to explicitly write down a representation of this thing, but that's what you can keep in mind. Very reminiscently to my definition of the algorithm from earlier, I'm going to want to use a geometric embedding of coalescent trees, which is due to Gavirushkin and Ramond. They call it tau space, and they create a separate copy of all possible branch lengths for each distinct topology, and there are a huge number of them. And they glue these separate positive orthents together along common faces. So by common faces, I mean these sorts of boundary points between 3 different topologies. So on the left-hand side of this diagram over here, I'm depicting tau space with 3 leaves. So there are 3 copies of a 2-dimensional positive orthent. The x-axis always tells me the time to the first merger event, the y-axis, whichever direction it happens to point in, tells me how long it takes to get from this first merger to the second. And this central x-axis over here is a point that belongs to all three orthents, where all three topologies coincide in a tree where all three leaves merge at once. And that's what I mean by this sort of notion of gluing the orthents together. You also end up in bigger trees with more leaves with second kind of boundaries where only two orthents meet, and that's where you have just two successive merger events like this, which change order. So that is also two different orthents glued at a common boundary. And this geometry will define my jump kernel Q as well, because you can imagine if I have a piecewise constant zigzag process running here and it hits this boundary, well, then it just progresses into one or the other of these boundaries of these other orthents. And as long as the probabilities of those progressions are set up in a way that obeys all of the conditions that I introduced on Q earlier, then I retain the correct stationary distribution. So this is a bigger illustration that I've grabbed from Gaviroshkin and Drummond explicitly. It shows 1/3 of tau space with 4 leaves. So you'd have to glue 3 copies of this sort of construction together in order to visualize what this tau space with 4 leaves looks like, and 5 and beyond, I think it's fair to say, it becomes pretty impossible. Okay, I just wanted to write down for illustration the fact that this sort of, given a tree with topology En and branch lengths Tn, I can write down the corresponding posterior distribution. So this will be my target density that I'm wanting to sample. In the interest of time, I don't think I'll unpick it very much, except you can recognize this first part as a Poisson kernel. It arises out of the fact that mutations fall on branches like a Poisson process. So this is a product over all branches, and for each branch you have a Poisson kernel, and M gamma is the number of mutations on that particular branch. The second one has the remaining sort of missing exponential term from the Poisson kernel, as well as those k choose 2 exponential random variables in there. You can write down the flip rates. They're not especially quick to evaluate. These are sums which have a number of terms that's linear in the number of observations, but they can be written down, they can be evaluated. And you can also sort of see from these expressions that in order to stabilize the corresponding flip velocities across many different values of I, so I here is running from 1 to n basically, you'll want to set up these velocities to roughly cancel with what comes through over here. Otherwise, you'll sample way more velocity flips in a particular coordinate than in a different one and impede your exploration of the state space. So you want to set up your velocities roughly in this way. The only thing I have to specify, which I already hinted at a little bit with the diagram, is what happens when I hit various boundaries. So my exit and entrance boundaries for this tau space are faces where one holding time is equal to 0, or where the mutation rate is 0. And my jump kernel I define to respect the kind of local geometry of the tau space that I showed you. There's those 2 different kinds of boundary events that you can have, either where 3 orthents intersect or just 2 orthents intersect. And in either case, it turns out that pi is continuous at these boundaries. Its gradient isn't, but pi is. And therefore, just crossing into a uniformly chosen adjacent topology satisfies all of the conditions on Q. So these things turn out to be particularly easy to design when you have a target which is continuous at your boundaries. And the only exceptions really are if your first holding time is 0, or if your mutation rate is 0, where you don't have any neighboring orthents, then you just reflect back into where you came from. That also satisfies all of the necessary requirements on Q. I have a simulation study on a data set, which is reasonably standard and well studied in Monte Carlo. I will breeze through that in the interest of time as well. This is sample size of 55, and essentially you can see that what's going on. Well, for looking at trace plots of mutation rates, so the marginal distribution of the mutation rate, the metropolis and the zigzag both seem to be doing reasonably okay. If you look instead at the underlying tree, so the latent tree, you can start seeing that zigzag is performing visibly better, has less autocorrelation, does a better job of exploring the state space. And this is a particularly unfair comparison because I've given the zigzag algorithm, I think, 7 times less computer time than metropolis. If I create artificial data sets which are bigger, so I've multiplied the sample size by 10, then the discrepancy becomes a lot more severe. Metropolis has fallen over and died. This is not reliable output, whereas zigzag is still able to mix reasonably well. And same thing if I increase the true underlying mutation rate, the same story follows. This is essentially modeling a situation in which the length of the DNA sequence has been multiplied by 10. So this is the slide I wanted to get to. What about a nuclear reactor? Well, we've seen similar pictures to this once or twice already throughout the last day and a half, and it seems fair to me to, so the take home for me has been that these kind of various rods and other boundaries that arise in the state space frequently correspond to discontinuities in the coefficients of the underlying transport equations. And so it seems fair to conjecture that there's probably some sort of discontinuities, or at least very big jumps in the target distribution at similar positions. And so if somehow you were able to evaluate the stationary distribution of, say, the neutron random walk pointwise up to a normalizing constant so that you could implement a zigzag algorithm on it, then the sort of cues that I've been talking about would be exactly the right tool for dealing with these these boundary points arising out of control rods and so on. So deciding if you hit a control rod point, whether you want to keep going into the interior of the rod or whether you want to reflect back out of it and so on, while maintaining the correct stationary distribution. And one thing which I've become to appreciate is it doesn't seem like there is a way to evaluate the stationary distribution even up to a normalizing constant. So that still appears to be very much an open problem, but that's something for which I don't have anything intelligent to say at this point. And with that, I'll thank you for your attention.
Thank you very much. Does anyone have any questions? Andy? Sorry, that was a clap rather than a hand up. Oh yeah, Andy does have a question. Great.
Yeah, hi Jere, thanks for the talk. I was wondering, is there anything you can say about the convergence in your case, like geometric ergodicity or anything like that?
Not immediately, at least. I expect, I mean, again, if you kind of restrict to this case where the set of discrete parameters is finite and you're mixing between them reasonably well, then you would expect that you get ergodicity to the same degree as you would get it for the kind of whatever the worst case restricted standard zigzag process is for a fixed discrete parameter. So yeah, in the case of finite discrete variables, you don't do any worse than the kind of standard setting of just one discrete variable. In the countable case, probably you could cook up situations where the discrete variables themselves break something further.
Mm-hmm. Yeah, and because I suspect your process probably also would fall into the kind of hypercoercivity framework, right, where you wouldn't be able to use kind of the obvious tricks as well.
Yeah, certainly if you don't introduce one of these kind of artificial positive flip rates everywhere, you're probably right.
Okay, thanks.
And Alex, do you have a question as well?
Yes, thanks for the talk. Thank you. So I'm just trying to get my head around this difference between the reversible and non-reversible. I mean, so I guess with reversible, I mean, if you were to try and do this with a reversible process like Metropolis Hastings, am I right in thinking that when you get to the boundary, I mean, I don't know if you can even do this, you would have this sort of process where it would sort of, I mean, it'd be like a diffusion crossing a boundary, is that right? You would sort of move back and forward between the two models until you get in the space, is that?
So you're talking about a Metropolis model, you mean, or?
Yes, so I guess, yeah, the difference between this, the sort of the zigzag and the Metropolis.
Yeah. So
the boundary.
Certainly for sort of practical Metropolis algorithms where you don't have non-local updates or something like that, you would expect that reversibility means that you sort of keep, wherever you are, you keep zigzagging for a bit until you diffuse away in one direction or another.
Yeah.
And this is, that's the kind of diffusive backtracking behavior that non-reversible methods are able to avoid, in that they keep going in the same direction until they see a reason to switch. Then they switch, and then they keep going in the new direction for a reasonable chunk of time again until there's until they see another negative gradient in the target distribution in the direction they're going, and that prompts them to switch, and so on and so forth.
Mm-hmm.
So yeah, a Metropolis algorithm might switch back and forth many times, whereas this is more able to just, if crossing the boundary doesn't look promising, then it's quite likely to reflect away, keep going away from that region again, whereas if it does look promising, then it'll just cross the boundary and move into the interior of the new part of the domain.
So will you tend to see reflection actually not just as it gets close to the boundary, but on the boundary? Is that right?
Well, yeah, certainly in the way that I've formulated it. So it depends on what the gradient of the target distribution is as you approach the boundary. If the target distribution is higher away from the boundary than it is at the boundary, then you might reflect earlier as well. Oh, I've lost some lights. Well, you can still see me, so that's the main thing. And yeah, if the gradient of the target distribution is increasing to the boundary, then you'll never reflect until you actually arrive at the boundary, and then it depends on, well, what the definition of this boundary jump kernel Q is.
Mm-hmm. Okay. Yeah. Okay. Thank you.
Are there any more questions? No. Okay. So thanks again, Jere. That was really interesting. And now